Thank you for the introduction, and thanks everybody for being here. And I'm very excited to tell you about some ideas that I was working on with my wonderful collaborators at SRI related to somewhat kind of futuristic security scenarios involving programmable networking. So I'm going to start by telling you a story that happened almost 20 years ago. In Greece, there was a silent patch being done to telecoms equipment, and as a result of this, some number of people were surveilled without legal justification. And what was particularly newsworthy of this at the time was that included amongst these people was the prime minister and high-ranking officials. But on the technical side, what was interesting was the way that this was carried out. So the equipment was produced by a manufacturer well reputed for producing flexible, field upgradable, hitless updatable equipment. But in this case, that was subverted, without the knowledge of the users of the network, and also without the knowledge of the operator of the network, right, who had a rather weak grasp of what was running on their equipment. So this provided food for thought for us, because we kind of in this community I suppose we have a rather positive nuance when we talk about programmability and networking, right? And albeit this story is from some time ago, and different network, different equipment, but the commonality there is in flexibility and programmability, right? And this was very interesting for us to ponder about, to try to see what can be learned from this, so that going forward we can build guardrails into how we program modern network equipment to avoid unwanted consequences, right? So that we can better understand and control what can be done on this equipment, and we can check it more opportunely and maybe curtail unwanted behaviors. So, as I said, we usually talk about programmability with a positive nuance, right? So we think of it in terms of convenient in-field updates without having to recall anything, right? Which would be more expensive, lower time to market, and also flexible implementation of features and extensions after equipment has been produced, right? And there has already been work done in exploring the risks of programmability to some extent, right? So specifically programmability in networking. So one of the things that we take away is that there's a larger scope for misconfiguration, right? So configuration is like the little sibling of programmability, right? Where there's a certain kind of blast radius that your misconfiguration can have. With programmability, particularly in the data plane, that blast radius can increase significantly. And there has been some work to understand what that might mean for different types of equipment. And if you look at the paper, there's also some elaboration and citation of the most representative works that we could find on the topic. What is particularly interesting is the trend points towards more programmability, not less programmability. And as we know, when things get more complex, they tend to get harder to control. And this is more programmability is going to exacerbate, is going to amplify the positives, but also potentially make worse the negatives that can arise from this. So we were motivated to carry out this work to try to get ahead of these potential negatives, right? To try to understand them before the fact, and to think about how, given that we are living in an age where network programmability is on the up, how can we steer that in a direction that can allow us to better control that programmability? And what I'm going to talk about is remote attestation. And there are other ways to try to mitigate these negatives, right? Including semantic analysis and verification. There's been a lot of really exciting work in that direction. And remote attestation is not a replacement for that, right? So both determining correctness through verification and also determining integrity through attestation are desirable to have, because something might be proved correct, but not actually be flashed onto a device, right? If it was mistakenly or deliberately replaced. So both are important, but to this point, remote attestation has not been given any or much attention, if at all, in programmable networking. So I'm going to start by telling you a bit about that, and then tell you about how we see it potentially merging with programmable networking. So in remote attestation, you answer the question, what happened to my data? What program processed it, right? And on what hardware? And you as a stakeholder, right, as the user of a network, even more so as the operator of a network, have some interest in understanding what is happening to your traffic. And in some cases, and for some users, there are also contracts that are signed to assure that traffic is handled in a certain way, right? So attestation helps provide transparency. We see this helping to provide transparency in this context. And remote attestation has had some traction in other domains, right? Particularly in kind of more beefy servers than the type of network processors that we use currently, and also is gaining traction in IoT, where one household can have potentially 50 devices in its network, and there is a keen interest in determining what those devices are doing in your network. So at the heart of it, remote attestation is about building and using evidence, right? Understanding who is doing what to what data. And it involves the tricky problem of bootstrapping trust amongst mutually distrustful actors. And we are in the fortunate position that this is not a new problem, right? Remote attestation has been thought of for a while. There are commercial products you can get for this. So we can benefit by learning from that and think about how to adapt it to this new setting. What I'm showing you in this diagram here is kind of some of the actors that are at play in remote attestation, right? It comes with its own vocabulary of who does what, right? And the standards clarify the responsibilities and the relationships between these actors. And this paper is about how do we migrate that to programmable network, right? So this is also similar in vein to one of the papers yesterday that talked about kind of an evolutionary path, right? So there are these two ideas, and how do we get them to merge? And the paper focuses on specification and mechanism, and it only scratches the surface. There's so much more that needs to be done on this, and I'll say a bit more about that at the end. So one of the things you'll find in the paper is kind of an initial mapping of the vocabulary, the ontology used in remote attestation to a programmable network setting, and a host of use cases that animates this. And a discussion, in addition to that, a discussion about how requirements and assurance and performance can be traded off. It is a complex space, right? Because in our field, we're often very concerned with performance, and that the performance might have to be lowered in order to make space for carrying out other in-network computations that give assurance about the integrity of programs and configurations. So as I mentioned in the paper, you'll find a variety of different use cases that motivate the usefulness of attestation and how attestation can help bring about appreciable benefits. In this talk, in the short talk, I'm only going to focus on the first one in a very, very quick running example, but do look at the paper for more. So when trying to map remote attestation to programmable networking, basically we end up with a task list of things that we need, right? So as we all know, topologies and heterogeneity can produce diversity that makes it challenging to reason about, right? Just yesterday we were talking about traffic engineering and how even in that somewhat clinical mathematical context, it can be very challenging to reason, let alone if we were to add on top of that, other demands to do with getting evidence on who did what to what packets at what time. Luckily for us, there is some prior work we can build on. So there is this language called Copeland that was developed over several years with inputs from many experts. That provides a verified tool chain for reasoning about the actors that I told you about in remote attestation and how they produce and process and check evidence. So here's an example of Copeland. Actually, here are two examples. And the paper kind of expands on what the syntax means a bit. But the one thing I'd like you to take away from this is that a really cool thing that Copeland provides is a way of reasoning about adversary confinement. So this is really useful because it allows us to reason about how to make the queries in different ways in order to avoid an adversary potentially providing misleading evidence. So the example in this case is for a bank as the relying party wanting to find out if its client is connecting from an end host that can be trusted, and the paper goes into showing that if you formulate the queries in different ways, you're still going to get evidence, but some evidence is more trustworthy than the other. So Copeland is great because it allows us to reason through this very kind of sticky space of options. But for us in a networking context, Copeland is not enough, right? So it was not designed specifically with our use cases in mind. So it does not know about parts and parts changing over time and placeability and places and reachability, which are bread and butter for networking, and which would be needed to map array cleanly to a programmable networking context. So what we thought would be a good combination is netcats, which is, as many of you know, is language for reasoning about processing in SDN, and it comes with primitives that could extend Copeland to give us what we need. And that's what the paper then goes on to describe. So it shows how these examples that were initially cached in Copeland can be extended using primitives from netcat to allow us to make up for those shortcomings I mentioned earlier. Okay, so this just scratched the surface of the topic, right? So in principle, the takeaways are programmability is good, but it's also a double-edged sword, right? So it potentially has a negative edge, and the Athens affair example was one of those rare appreciable examples of how that can be consequential. We're focusing here on specification and mechanism, but there's a lot more to be done in this topic, and ongoing work involves stress testing more use cases and scoping out the implementation and formalizing this hybrid formal language that I described earlier. Now, since yesterday somebody mentioned that they're looking to do a PhD, I just wanted to quickly mention that I have the opposite announcement. I'm looking to recruit PhD students, so if you know of someone who's interested, I'm unabashedly making the call right now. And these are some of the wonderful students I've worked with over the course of this last year at Illinois Tech. And yeah, happy to talk more, and why not, come visit. We're very accessible close to Chicago. So thank you.
So Tango?
Hey, so you started by talking about the Athens affair, right? So how do you attest to the absence of packets being sent or being copied? And also, why does programmability have anything to do with attestation? Like, we've had concerns about what are so why is attestation tied to programmability?
Great question. So there's a two-part question, right? So one thing is, how can you reason about whether packets are leaving the network, right? And in the paper, we have a threat model section that addresses that very point. The answer is we can't, because somebody might install an optical tap, and there is no way of knowing then that traffic has been duplicated, right?
Sure. So does this work prevent the Athens affair, which you've been using as your?
So the Athens affair was a bit different, right? So there wasn't a kind of a passive attack, but rather there was an active update done to the software in a switch to activate some other features. So the overlap between this and the Athens affair was that using remote attestation, we'd have a better way of noticing, we have a way of noticing that the software that we thought is running on the device is not the same as the one that is actually running there. So it would provide early warning to this. And maybe this is a configuration glitch, that somebody will see to. Maybe it's something harmless like that, but maybe it isn't. So that's the key kind of overlap between the two, right? So the operator there didn't know it was running. And maybe interestingly, the users didn't know what was running, right? And users of networks, maybe we are accustomed, we're inured to that. But maybe that's something that could change, right? So as one of the talks mentioned yesterday, providing more agency to users, to their browsers, maybe to influence how their traffic is handled, is a resonant idea. That maybe we can have better expectations on the security and privacy of our traffic. And one way to gain information about that is through finding out who is doing what to our traffic along the way, right? So I see kind of a sibling, resonance there.
So can I ask the next speaker to set up while I have another question for you, Nick, in the meantime. So what do you say about the usability of these techniques? Like cleaning algebra is not that easy to learn. So
yeah. I think that's part of the problem. There was another interesting question yesterday in relation to in relation to the browser policy thing, right? Writing a policy is hard, and end users aren't very good at that. I think a model that might work is kind of the SC Linux model, where either a government entity or an employer in a BYOD sort of way, or maybe some other NGOs would write policies that users could then use, since, as you say, it can be very technical, right? So I think this provides the means to an end, but it also would require input of experts not writing this policy.
okay. So our next speaker is going to present a paper on distributed verification of networks. He is Frank Lee from IBM. He's in the distributed AI group, and he received his PhD from Carnegie Mellon University. With that.
Thank you very much. So this presentation will be on network and check itself, scaling data plane checking with the distributed on-device verification. This work is done in collaboration with Xiao Jiang, Ruidi Wang, Shenyang Huang, and Yuxing Wang. Unfortunately, the first authors could not attend because of visa problems. Data plane verification is an active research area. In the recent years, there have been a number of papers, very interesting ideas. And the main step typically consists in first collecting the feed and the echo from the network devices, sending them to a verifier in order to check that the network forwarding behavior comply to desired properties. And the verifier typically rely on a cluster of servers. For performance reason, advanced data structures and algorithms have been proposed. However, most of the solutions rely on this centralized approach, which present limitation. For example, the verifier can be a single point of failure and also can present performance bottleneck. So in this paper, we investigate the question, can we offload the verification to distributed computation on the network devices? So the idea, we want to remove the single point of failure and the performance bottleneck, and instead we want to push down the task on the network device itself. So this raises a number of challenges. First, what invariants can be checked in a distributed manner? A recent SICOM paper started to investigate that question and propose a concept of local contracts that can be verified for different devices, but they focus on the property of shortest path availability and also exploited the specific topology in data centers. In this paper, we want to go beyond that. We want to see if we can extend the scope of property we can verify and make it more general to other topology as well. Second, how can we make the on-device task lightweight? This is motivated by the fact that network devices have limited resources, CPU, memories, and they already have a number of processes that need to run, such as BGP, OSPF, and other routing protocols. Finally, how can we make the devices exchange the results in a correct and efficient manner? So in order to address those challenges, the first one, we show that we can verify, we can extend the scope of properties, and we can verify what we call single path invariants. These include reachability, waypoint, multicast, and anycast. Intuitively, basically, we can verify property that can be expressed as a regular expression. For the second question, how can we make the on-device task lightweight? For that, we show that we can transform the verification task into a counting problem in the DAG. And this allows simple, lightweight tasks to be run on the network devices. Third, we show that if we propagate the results along the DAG, this allows for correct, efficient incremental verification. So to illustrate the idea, let's assume the following topology. On the bottom, we have a simple topology, and let's assume the following requirement. We want all packets entering the network through S and forwarded to 10/23 to reach D. And the waypoint requirement will be that they need also to traverse point W. So we can see in the box that like we can express it as a regular expression as star W star D. So to achieve that, we proceed in 2 steps. First, we build upon the concept of product graph that was proposed by Propane and Contra. So Propane and Contra explained that like taking the product of the requirement and the topology, we can have a graph that represent all the valid paths in the network. Then in a second step, we take into account the network forwarding behavior from the network devices. So we combine the product graph with the feed and the echo from network devices in order to answer the question, given a packet P, can the network deliver a satisfactory number of copies to the destination? To further illustrate it, so the way we proceed, we initialize the count to 1 at the destination. Then we proceed in a backward manner in the product graph. So for example, in this case, from D, we look at the upstream node, it would be, let's say, W and C. At W, we look at the forwarding graph, or we look at the feed, and we see that it will forward all the packet to the destination to C instead of D. As such, we update the count to 0. In contrast, C will forward all the packets to the target destination, to the target prefix to D, so we update the count to 1. In the same manner, we backpropagate all the way to the source. At this point, we see that there are 2 entries at the source, P3 with a count of 1 and P2 with a count of either 0 or 1. So the presence of 0 points to the fact that we can have errors. If we go back in this case, we'll see that A can forward the packet to either B or W. If it forward to B, it will forward to C, and we go to D directly. So in this case, that path will not satisfy the requirement of the waypoint that the packet must go to W. So in this illustration, we show how we can verify, for example, reachability. In the paper, we go more into the details and illustrate other properties such as multicast, anycast, different ingress consistent reachability, and all shortest path availability. There's also the following link where we have some demos to illustrate the different properties. So in addition to the properties, we also conducted some preliminary evaluation. We considered 5 topology and we compare with existing centralized data plane verification, such as atomic predicate, AP keep, and veriflow. On the top, we first consider what we call like burst update. So we assume all the rules need to be installed. And in this case, our proposal on the rightmost, we can see that we verify the property of reachability, and we report the time to complete all the verification. So we want the shortest amount of time. In this case, you can indeed achieve the shortest amount of time. Then in the next table, instead we consider incremental updates. So we want to verify, we randomly generate 10,000 rules that we want to sequentially verify. So we first report the percentage of rules that can be properly satisfied under 10 milliseconds, or we also report the 80% quantile. And for both cases, we again see that the proposed approach can achieve the shortest amount of time. In addition to those evaluation, we also conducted micro benchmark to verify that the proposed approach is feasible and can run on commodity switch. More specifically, we look at the processing time, the utilized memory and CPU for both initialization, for example, to compute the local equivalent class, and also to process message updates. Because of time constraint, I won't be able to go too much into detail, but they are in the papers. So So finally, there are still a number of like open research questions. For example, we want to expand the scope of property we can verify. We show that we can verify single path invariance, and we question how we can handle path comparison invariance. By that, we mean like if we have the packet space, for different packet space, can we verify, like, for example, properties about the path that would be useful for route symmetry. Also, earlier work in that space have pointed out like some network devices may transform the packet, for example, NAT. So in this case, how can we handle it? We also briefly discussed about incremental deployment. And finally, I think one of the open research direction is how we can handle data plane verification in the interdomain case. In conclusion, in this paper, we investigated distributed on-device data plane verification, which can be essentially be proposed as a value-added service to vendors. We show promising preliminary results, and we also have like more interactive video at the following link. The prototype run on Sonic and has been proposed as a feature. And then finally, we identify research questions. I thank you very much for your attention, and I'll be very happy to answer a question you might have.
So we have time for 1 or 2 questions, if anybody has one.
Yeah, hi, very cool work. This is a way talk from Rice. I think your example shows it looks like a deterministic automaton. So can you support logics that looks like a non-deterministic automaton?
That's a great question. So indeterministic can be like for different, it can be like either like a random rules, or it can be, for example, like link failures, right?
Yeah.
So when we compute, like, for example, the product graph, we assume that the link in a certain way, and then, for example, in the meantime, a certain link can fail. That's a great question, exactly. So we touch upon that in the paper. We definitely say that we can, the device, when they receive the product graph and that some links fails, we can set, for example, the count to 0. So there are some cases we can still handle that. But definitely, I think that that's a very good question. Thank you very much.
Yeah, thank you. Another
Yes.
question. So how hard do you think you can support multipass? Do you think it's
Multipath?
Yeah.
You have specific, I think they can, as long as we can describe into a regular expression, we can compute a product graph, and hopefully we can satisfy it. Maybe we can discuss offline to see some use case after that.
Yep.
I think it was a very good like scenario. Thank you very much.
Yeah, thank you.
Yes.
And if you want to.
I just want to know, like, what exactly is the motivation for distributing the verification tasks? Like, typically, like, yeah, they'll gather all the configurations at a central location and verify them. I think you briefly mentioned that, like, verifier can become a single point of failure, but like, it's not, verifier is not necessarily a user-facing component, and so like, what are we benefiting from like distributing this task?
Right, that's a great question as well. So the idea would be like, in addition to being a single point of failure, it can be a performance bottleneck. So the idea is like when we have a rule update, we want to be able to verify as quickly as possible, right? So we can, for example, make action on, if you can cause like loops or like enrichability, we can act on it as soon as possible. And we show that in the evaluation that like by distributing it, like the range of property right now is more limited, but then like for those that we can satisfy, we can make it in much shorter amount of time. So I think that there was also a lot of recent work in the past, I think like Hotnet 2 years ago, that how to, like, if we have some rules that can conflict, how we can like repair them basically. I think that would be a very good use case. Does it make sense?
I'm just trying to understand why should switches do this task? Like you can, parallelization is a separate thing from making the switches do this task, right? You can still have a cluster of verify, like
Definitely.
compute engines.
I completely agree, right?
servers.
So I think there was like some works that investigate like, can we instead distribute the work? I think there was Libra who take advantage of the map reduce case. So they want to like distribute it and put to the different reducer. And there was like the paper I mentioned, SICOM 2019, that also want to distribute the work. Since we submitted the paper, we have been doing more evaluation, and we found that we can still also outperform those one as well. We can discuss, like, I can go more into the details, like about the performance. So I think performance is a one main driver. Exactly.
Okay, yeah, we can discuss more.
Perfect, sounds great. Thank you very much for your comments.
Let's thank the speaker again. So our next talk is going to be talking about how to program our networks better. The speaker is going to be Devnil Sur. He's a senior software engineer at VMware. He got his bachelor's and master's at the computer science department at Stanford, and he has an NSF grant for 3 years, and he's looking for a PhD. So Nick, you just said you're looking for PhD students. This might be the person for you.
This work? Testing, perfect. So hi, my name is Devnil. I'll be presenting full stack SDN, and this is joint work with Mihai, Ben, and Leonid at VMware Research. So as mentioned, I'm applying to grad school with 3 years of funding. If you're hiring, I'd love to talk. So let's start with the question, how do we usually organize software-defined networks? So we usually divide the network into the management, control, and data planes, and we can analogize these to a light bulb. So the management plane is setting a high-level configuration, and it's like a dimmer switch, which sets a policy on how much light you want. And then the control plane is controlling forwarding throughout the network. And it's like the hidden electronics in your wall that are translating the switch's intent into the voltage level. And then finally, the data plane processes packets, and it's like when your bulb lights up the amount you want. So usually, these are programmed as 3 separate entities, and it's up to the developer to figure out how they fit together. We think this creates a few problems in real deployed systems. So we've noticed 2 big types of problems, scalability and correctness. We have many empirical and anecdotal examples in the paper, but I'll provide some high-level motivations. So the first is scalability. In a deployed network, changes happen frequently, whether it's because of admin-level directives from your management plane or it's because of messages from your data plane. And we don't think that you should have to recompute and redistribute the entire network state. And instead, it should just be the incremental changes. But that's really hard to do in Java or C++, which are the languages that are often used for SDN controllers. It requires unnatural style, and then your developer has to do a lot of programming around edge cases. And then the second big problem that we see is one of correctness. So when you are able to add those new network features, you have to do a lot of collaboration between teams and code bases that are written in really different languages. And then that creates sprawl because you're adding more OpenFlow flows or P4 program fragments. You have to figure out how to stitch all of these together at runtime, and it just becomes more and more expensive as your program grows. We think there has to be a simpler way forward. So here's our big vision for software-defined networking. Ideally, this is the holy grail. You'd be able to write one program at the top and then program all 3 planes. So we don't quite get there, but we think our approach saves a lot of developer time, and it has significant performance benefits for the stuff we just talked about. So here's our approach, which we've nicknamed NERPA. And we make 2 high-level arguments with implications for how we program networks at scale. First, we think an automatically incremental control plane can improve scalability. So incrementality would help the control plane scale in production, but as mentioned, it's really hard to do in Java or C++. And we think new work on incremental and streaming computation engines in the databases community provides simple but powerful abstractions to write the automatically incremental code. So our team has been working on one such language, which is called differential data log or DDlog. And in our prototype, we use this to write the control plane, and it uses relational database-like abstractions. Second, we argue that type checking all 3 planes together helps construct a complete end-to-end program. So here the developer provides 3 programs. You have a database schema for the management plane, a P4 program for the data plane, and then in the middle, a differential data log program for the control plane. So crucially, we have tooling that generates the relations you use in that control plane program from the schema and from the data plane program. We also generate the glue code that's used to move the data between those different planes. So while past work might have used new SDN languages, our argument is that instead we should leverage the state of art that's emerging and instead make it really easy to interoperate these things when we're programming the system. So, we've talked about our vision. Let's see what this looks like plane by plane. So first in the management plane, we represent and persist network state as database relations or tables. So you can have tables of switches, links, hosts, policies, and the like. And the sysadmin will use the database APIs to read and write the network state, and mostly to express the desired state. The same APIs are then used to communicate the changes to and from the network control plane. So the management plane finds out about the realized state. So this has this really nice cycle that makes sure that your sysadmin knows what's going on. Next, we have the network control plane. So here's where we really start seeing the new changes from these database principles. So we express the network state as database views. You have queries that compute those views as functions of the realized and of the desired state. And we argue that those contents should be automatically and incrementally maintained. So then when you have incremental updates to those views, the outputs are then pushed to the data plane. Finally, we have the programmable data plane, which is used for high performance packet processing. And a dispatch sits between the control and data planes. This translates the incremental output changes into table entries for the programmable switch. And you see at the bottom that we monitor the switch for notifications, packets, and other messages that are sent back to the control plane. So now we've talked about each plane. Let's see how we would program an entire system. So here's how all these pieces fit together in our current prototype. When you start at the top, the user is writing 3 programs. Usually you first model the network entities in the database schema, and then you also have your P4 program, which you're using to define packet processing. Then our tools will generate the input and output relations from those 2 ends. Now you have all those relations and you put them together to write the control plane program in something like ddlog. So then when the ddlog program gets compiled, as you see in the middle, it compiles to Rust, and this is run within a larger Rust program that's used for synchronizing state. So that program is talking to your management plane and your data plane, in our case, OBSDB and the P4 switch. So it's reading any configuration changes from OBSDB. It writes new table entries to the switch using the P4 runtime API, and then you pass the messages between the planes as needed. So we argue again that the type generation and common tooling really helps with programming and maintaining your software-defined network. So now when you're writing the control plane, you're trying to maintain it, you're not guessing about the abstractions that you have. Instead, you've generated them, you know exactly what they look like, and your job is just figuring out how do I connect point A to point B with really simple expressions of what this should end up looking like. So now let's talk about our last piece, which is some of this incremental work and how we think we can make it easier to write the control plane. So usually when you do a query, it looks like this. You're querying the input tables for some slice of the data that gets computed over the entire input, and then you get some output tables. That's how we usually use databases and networks, and it means there's a whole lot of information we try to push when we have some changes. Now in our vision, we would have incremental queries, and the control plane can scale through incremental computation. So this is really where we leverage a lot of those databases community changes, which has driven big advances in streaming computation techniques like data flow in recent years. So in data flow, you would represent your computation as a directed graph. A node represents a step in the computation, and then data flows along the edges. And there's newer work like differential data flow, which takes us one more step, and each node will just maintain the collection of differences that's used to generate incremental updates. So differential data log is a language that builds directly on those technologies, and it allows the queries to become incremental. So we add a powerful type system as well as some relational and procedural abstractions that you can use to specify the desired computation. I'll show an example of what this looks like in a slide. The big takeaway is that in ddlog and languages like it, the programmer is not writing the incremental algorithm. Instead, they're just making a high-level specification of what they want the features to look like through declarative rules. And then the compiler will make that specification incremental. So then, and when you're at runtime in your system, the ddlog program will take a stream of updates to the inputs and then follow the rules to output a bunch of rules too. And then those all get pushed to the network. So this slide shows a really simple example, which is what routing can look like in ddlog. So you express the logical connections, and then you trust that the compiler will generate the incremental program. And so as you can see, these languages end up really well suited for the sorts of graph computations we frequently see in networks, because you've just expressed how everything fits together. And now let's say you have a link that changes. Now you're just changing that incremental update, and then that's what actually gets pushed to the switch. So as you can see, these programs end up being an order of magnitude shorter than their C++ or Java equivalents. This combination of simplicity and scalability provides the last piece in our puzzle. And it means that the network programmer really gets to focus on expressing rules rather than having to debug corner cases. So we've implemented many of these pieces, and others are still in flight. And you can see some preliminary findings around scalability and correctness in the paper. So the major repo that you want to look at if you want to play around with any of this stuff is the NERPA repo. This implements the system I sketched out above, along with some examples and tests. And it also includes the prototype P4 to OpenFlow compiler, which we're hoping to use for some high-speed switching. So next, the ddlog repo has the program language implementation, compiler, and many helpful examples. And then OVN, the Open Virtual Network Controller, is the main example we're working on now. And it also includes OBSDB, which is what we're using for the management plane. Cool. So in conclusion, we think our approach really helps pave the way to full stack SDN. By treating the network as one heterogeneous distributed system, rather than fiddling around with parts, we think that you can program the entire network stack. And so we've tried to make this as easy as possible. We type check the stack, we automate data movement, and we operate on incremental changes wherever we can. So we hope that these high-level insights, which are using some powerful abstractions, can really simplify how we think about and develop SDN moving forward. Thank you.
So we have time for 1 or 2 questions.
Hi, Archie from ByteDance. This was a great talk. One question that I had was that I've heard of ddlog being used as incremental verifiers for control plane.
Yeah.
This is one of the first I've heard about just programming it. So wanted to know, do you have any comments on limitations of its expressiveness in modeling the control plane?
Yeah, that's a great question. So I think, so the paper delves into this a little bit. I think the key takeaway here is that you can make anything incremental, but it begs the question if you should make anything incremental. So for example, there's been some work on using ddlog and OVN, and then there were some benchmarks in OVN that ddlog just didn't provide improvement on. And the reason that was the case was because the performance bottleneck there was not one of, oh, we have new changes, can we push these? Instead, it just wasn't an incremental problem. And so, if you have parts of the control plane that aren't actually about new snapshots that you want to update, it's not going to help.
Yeah, I have one similar question. It's I like your idea, which is to view the updates as a database. I'm thinking, how did you mapping the atomic operation between the database and the real hardware?
Yeah, so this is a good question. It definitely begs the question of like knowing your API as well, and it's probably the job of the sysadmin to understand what the limitations look like between the OBSDB API and the P4 runtime API, and where those things might go out of sync. But it is certainly something we're working on as we're building the real system and making sure we can quantify what those performance differences might look like when you have distributed communication.
Yeah, one thing I want to specifically mention is that in data plane, something can be atomic. It's like multi-stage register. You can change it all at once.
Right.
So that can be atomic, and I think it may be helpful if you can represent this in the database.
Nice. Let's talk about this more offline. This sounds really cool.
Yep.
Yeah.
Okay. Thank you.
Let's thank the speaker again. So next we have Henry Birch Lee. He is a PhD student a research software engineer at Princeton, and he's going to talk to us about cooperative routing at the edge through BGP incentives.
So hi, my name is Henry Burge Lee from Princeton University. Today I'm going to present It Takes Two to Tango, cooperative edge-to-edge routing. So I want to start my presentation by asking a question. Do you think the internet is good enough to serve real-time applications? And before you answer that, I'll say that if you're at this conference from a major content provider network, you're probably already thinking no. And why do I say that? Largely because network performance is being increasingly offered as a paid service. So we actually see this taking many forms, one of which is edge computing. That is putting performance critical services at or near edge networks. The other one is network as a service offerings. So these are on-demand products that offer reserved bandwidth, reliable links, point-to-point links that you can spin up on demand. But all of this actually comes at a bit of a cost. So first off, it's sort of a social cost of increased consolidation. This is a map of AWS and Google's edge networks. As you can see, they have tons of edge nodes spread all around the world, which is really what you need with edge computing to reach a global user base and actually have that content right next door. But only hypergiants can really afford these types of edge networks. On the network as a service side, it can actually get quite pricey. This is the price for a 10G line from Chicago to New York. And this is not a full internet upstream connection. This is simply a reserved bandwidth line that goes to one point, New York City. And they're quoting me at $1,700 a month. So obviously, if you need a lot of these, this can start to add up. And that also makes it harder for smaller corporations to kind of get into the game. So with all that in mind, I raised the question, what would it take for the good old internet to actually serve real-time applications? And I first want to touch upon a topic that Adrian went fairly in depth on yesterday, which is path diversity. Traditional internet routing, which with BGP, doesn't do a great job of exposing all available paths. So in this diagram, edge 1 and edge 2 are edge networks. They want to communicate with each other. And they actually have 4 paths through the core of the internet topology. But edge 1 only has a single upstream, AS5. And it's essentially at the mercy of whatever route AS5 chooses to pick. And it has one forwarding decision, send your traffic to AS5. So it can only find one of the paths. Now, edge 2 is in a much better position, being multi-homed. It has 2 upstream links. And it actually has a body of multi-home route control work that it can draw upon. But if we look at edge 2, it can only make the first hop of the forwarding decision through the topology. And there are actually 4 available paths, but it's only able to pick between 2 of them because it can only send us traffic to either AS2 or AS4. So with this in mind, we're clearly not able to actually explore that many paths through the core of the internet. The other problem comes in the form of accurate measurements. So let's imagine an edge network that wants to measure path performance to make an optimized forward routing decision. So it's sending packets and it wants to pick what route to send the packets on to the other edge. And what it really cares about is the path performance along the path of this green arrow. So that's the forward data path to the other edge across the wide area. But if this edge was actually to take performance measurements, what would it actually see? Well, it's going to see round trip time, which in its name implies that you're seeing both the forward and the reverse path getting added together. So you have a noise signal from the reverse path that you don't actually want when you're making a routing decision. But if we actually think about the problem, it gets worse. Because round trip time means that the packets actually have to go all the way to the other end host and come all the way back, which means that you're actually going into and out of that other edge network, which might be an access network or a wireless access network like this diagram. So you're introducing another very large noise and uncertainty signal, which honestly in the wireless case can be substantial, even larger than the wide area component. And then finally, I think this is a great tie-in with another great paper from the last session yesterday, Gina's paper about Quack. When you're monitoring RTT, you're actually depending on what the layer 4 protocol and the end host implementations are doing. So you can imagine this TCP monitoring, it's normally data to ACK round trip time. Right off the bat, if you have delayed ACK, you have to account for that in your network hardware. So that's an end host implementation choice. And then if the end host is running quick, but is not quacking, you do not get the round trip times out of quick the same way you do in TCP. So all of a sudden, we're highly dependent on the inner protocols. And this, remember, this is largely an IP layer 3 forwarding decision we're trying to make. So this makes it really hard to actually optimize internet routing. But I think there's a hope. And that hope comes in the form of Tango. This is a picture of my spouse and I dancing tango. And as you can see, it's a very tight dance with tight cooperation and collaboration between the 2 dancers. And this is Tango on the internet. And what I'm proposing is tight collaboration between 2 edge networks to really get the most out of the core of the internet. So right off the bat, let's re-examine some of the classic challenges with inter-domain route optimization. First off, path diversity. It turns out that edges can collaboratively use BGP tricks to coax more routes out of the core of the internet. So what do I mean by this? BGP is largely thought of as a one path per destination routing protocol. This is actually untrue. BGP is a one path per a prefix routing protocol. There's no rule saying that a destination cannot have multiple IP prefixes that it can be used, that you can reach it at. In fact, most ASs nowadays announce many IP prefixes for a variety of reasons. And in this diagram, edge 2 has 4 IPv6 prefixes that it can use and it can be reached at. Now, it can actually use BGP communities, which are tags on BGP announcements that indicate how they should be propagated, to cause these 4 different IP prefixes to actually propagate over different interdomain paths in the core of the internet, and not just an immediate next hop decision. So in this manner, Edge 2 can explore all 4 different paths through the core with different IP prefixes. Now all Edge 1 has to do when sending a packet to Edge 2 is pick what IP prefix it would like to send to, and it's thus picking a path all the way through the core of the internet and picking between all 4 available paths. So that vastly improves path diversity. I also want to talk about measurements. Once we start thinking about the 2 edges collaborating, accurate measurements become much easier. So right off the bat, we can take protocol agnostic measurements by encapsulating packets in a special Tango header. So we don't care about what's happening in the inner protocols. We now have our own measurement headers. We can also, by having a node at both ends, we can now take one-way measurements instead of round-trip measurements. And finally, by placing these measurement nodes right at the edge of the wide area component of the network, we can eliminate all of that access network uncertainty. Just to make this clear, we can have a Tango node running at the 2 edge networks. And you can implement this in programmable switches, which can add this measurement header at line rate, even on large packet loads. And when we're measuring this, we're only looking at the wide area one-way component of the traffic. And then finally, all of this doesn't depend on application behavior because we're adding a header on top of the packets. And on top of all of this, we've accomplished all of this without changing anything in the core of the internet. So even though we're using BGP communities, these are actually standardly supported by many ISPs today. And nobody in the middle of the internet needs to be aware of Tango. And that's really exciting because it leads to easy incremental deployability. All you need to run Tango is 2 nodes that want to talk to each other. It's also really exciting for me because we were actually able to build a prototype of this using a real cloud provider. Using the cloud provider Vultr, we made BGP announcements from the New York and Los Angeles data centers to explore available paths. We're able to find 4 paths in each direction where normally we would have only had 1 path to send traffic between the 2 data centers. And then finally, we wrote an eBPF program that added measurement headers to packets and let us measure one-way delays. Right off the bat, what we found is that the BGP default path that our data center provider had previously given us had a 30% higher latency than the actual optimal path. Looking at this graph, it has latency in milliseconds on the y-axis, ranging from 25 to 50, and it has time in hours on the x-axis. It shows a 24-hour trace of our data. The blue path is the default path that we had from our data center provider. And the green path at the bottom with much lower latency is the path we're able to find with Tango. But this is more than simply a static optimization problem. So it's not about just finding the best path, updating your BGP announcements and working with that. We're actually able to dynamically switch paths. And we found good reason to do so. Looking at the data, we found these occasional periods of instability where potentially our most performant path, like this green one, would degrade and all of a sudden have latency spikes. And during these periods, you'd often be able to find an alternate stable path that you could send your traffic on instead. And this is really important for real-time applications that are particularly tail latency sensitive. So in this manner, you can actually dynamically route around these periods of instability that people often complain about with the public internet. So I want to end by saying that 2 ends can cooperatively get more out of the internet. They can find better path diversity by hacking BGP communities, and they can take accurate measurements with end-to-end monitoring. Finally, our preliminary results show that there's actually a big advantage to dynamic and optimized routing. So I want to thank everyone for your time and end by taking any questions.
Great talk. You can also do amazing tomography. Like if you have all the edge networks exchange measurements, you know, they can kind of, they can do tomography on the internet scale, right? And
Yes.
be able to localize faults.
Yeah, we think that's really awesome. This presentation is largely focusing on kind of what we call our Tango of 2 setup, but we're actually working right now on exactly what you're saying, sort of Tango of N, where you can have an N node cluster. They have sort of common, but also as distinct paths. And then you can start doing that great type of work where you correlate faults.
And another quick question, perhaps a bit more philosophical. So should we be trying to trick BGP, or should we be trying to convince, the world to go the Cyan way and have, ISPs expose path selection to users?
So that's a great question. So I think what I'd first say is that largely what we're offering is a subset of Cyan. Cyan is able to offer more advanced features, given that it's really a clean slate with people not running BGP, and it requires upgrade from the middle of the internet as well to make those paths available. This work is really about something that we can sort of deploy at a lot of nodes today and backward compatibility. Largely as to whether we're kind of about tricking BGP or going to Cyan, I don't think they're mutually exclusive. Cyan is wonderful, but it's also, it takes a long time to roll something new out like that. BGP is what we have today. And I think even in a largely Cyan world, you could still see, it might be hard to make the entire world Cyan. BGP is what we have. BGP communities are a increasingly more and more popular tool for controlling BGP route propagation. So I think largely I don't see these two much in contrast. I think there are initiatives happening at the same time, because even while Cyan is being rolled out, we're still going to want to control and improve BGP routing.
Aditya.
Hi, nice talk. I'm Aditya Akela from UT Austin. So I was one of those people who suffered through BGP in the early 2000s and trying to salvage whatever performance we could get out of BGP. Back when we did this work a while ago, we used to see improvements in latency that were like tens of milliseconds, very significant improvement in latency from being able to select among multiple paths. Your improvements are good, but it's on the order of maybe 5 to 10 milliseconds in the paths that you were showing. So I guess like my comment is are things really that bad today from a performance perspective? It seems like maybe something like the flattening of the internet hierarchy is already giving you reasonably good paths, and there's not really a whole lot of sort of improvement in performance that you can expect from there. Maybe really it's about availability and having multiple paths. Maybe there's better scope for picking a path that's available. So I'm curious, like, what you see as sort of the ultimate tangible benefit that you can get from this?
Yeah, so I think that's a really great question. I think there are multiple levels of it. First of all, there is an availability angle that we can find paths. I also do a lot of work on BGP hijacks. So if a path appears to be hijacked, you'd want to start routing around that right away. From the purely performance angle, though, I would definitely challenge the question that the flattening of the internet is solving this problem at multiple levels. First off, interdomain routing does an atrocious job of picking a performant path. There are many proposals, but it's very hard to accurately communicate performance informations between domains. So there's communities, ingress, egress communities, there's meds. All of these are these sort of very high level control plane operator defined metrics. They don't actually track real path performance. And when you look at interdomain paths, you find very often that they're taking, even to a nearby data center, a highly suboptimal path. Without getting too much into the details, the university on that has a behavior where it's about half the time inflating its connection to nearby data centers by double or triple, just because of a pathing problem. And so I think this idea that somehow just by moving the content closer, we're going to start picking good paths, I don't believe in that, because there aren't great mechanisms in the control plane right now to pick good paths. And even if your content is very close, there are still bad paths that you can pick to it. And then I think also then the other layer of this is just the flattening of the internet. That's once again just sort of assuming a universe where the hypergiants have dominated the world and everybody can put their content right next door. And I think Adrian's point that if you look at bytes, yes, a lot of bytes go very short, but if you look at connections, it's still really important to optimize truly interdomain routed connections.
Thank you.
So before the next question is asked, can I ask the panelists to start assembling here so we save time a little bit to get more questions?
Hello, this is Jiaxin Lin from UT Austin. This is a great work, and I have a very small question regarding how you measure the one-way delay between two edges. Do you assume there is a clock synchronization protocol running between them?
That's a great question. So no, we did not deal with clock synchronization. Largely our justification for that, especially in the Tango of 2 case, is that we have strictly 2 agents. And these are paths between the same two agents. So if there's a clock offset, that's going to be a constant between the two of them, and we can still measure accurate relative one-way delays. you're absolutely right that to make those absolute values have meaning, that requires clock synchronization, and we didn't address that at this time.
Yeah, but yeah, because I'm thinking maybe the clock offset may also shift with time, like, so your clock.
Yes, the clock offsets will shift with time, but not at like the millisecond level. It's like if there's a 10 millisecond clock offset on this path and a 20 millisecond, if the subtraction is 10 milliseconds on this path and 20 milliseconds on that path, and we're sending these packets like at millisecond levels, I don't think the clock offset shifted 10 milliseconds in between two packets that were 1 millisecond apart.
That makes sense. Thank you.
So can we thank the speaker again? So we have Maria Patsalecki representing the last talk, and sorry, I never got your name.
Hi, Budil. I work together with Debnil on the full stack SDN project.
Okay, so questions for the panel? Go ahead.
Yeah, thanks. This is more a question just for the last talk, the Tango talk. I was wondering about if everyone were to use this, what would happen to convergence and scalability of the internet, especially in IPv6, also the size of highly fragmented address spaces. Right. So I think the scalability may be affected, not just due to the convergence, increased convergence times, but also TCAMs and their use for IPv6. Right.
So thank you for the question. So basically, with respect to convergence,
yeah.
All right, so that's a great question. So with respect to convergence, this is not something we deal with because we are assuming that we're in a smaller scale. So we're just interested in the applications that you're interested in improving their latency. You don't have that much of data. But with respect to the IPv6, that's a great question. I very much agree with that. But what we're trying to actually achieve is that not all ASs would actually have IPv4 prefixes that they could use to basically have different prefixes that are being advertised. So basically, because our main concern with Tango is giving other ASs the ability to actually have more path diversity, we didn't want to rely on IPv4. And I very much agree with what you're saying that, okay, TCAM and we have a problem with the routing sizes. But on the other end, this is a solution more for ASs that would not have the luxury of having multiple IPv4 prefixes that they could advertise in a different way or have it to be. Does this answer your question?
Right, but I think there are a lot of aspects of scalability that will come into play here if everyone were to do this to get these multiple paths. And it's an issue because BGP is already at the edge of also scalability with respect to convergence time. And we've also seen for IPv6, the forwarding tables sizes have been getting to the limit of what current TCAMs can handle. And of course, you can build them bigger, but there's also going to be a power trade-off as well.
I agree with that. Two basic points there. One is the fact that IPv4 is actually not fragmented, but just by the fact that we're actually using IPv6, we might be able to reduce the advertisements that we'll actually do. And the second point is that this is not a solution that we envision that every single AS will do it. So if we were indeed in an ecosystem where every single AS care so much for their performance and their path selection, then would be better, obviously. But we're mostly looking at ASs that want to deploy it tomorrow at very little cost.
Go ahead.
Yep, I do a little bit of work stealing to cut in the line. Okay, so I also have a question for the Tango expert. Do you think if you service scale, you may want to use multiple server for one Tango, so one Tango content multiple servers? Do you think that will affect the one-way delay measurement? Because if multiple servers clock not synchronized, like Justin said, that will also lead to inaccurate RDT estimation.
Just a clarification, do you mean multiple servers, single edge, or multiple senders? So we are imagining 110 nodes.
Oh, single edge. Yeah.
Gotcha. So actually, we don't really have this problem, and that's because we are envisioning Tango being deployed on programmable data planes. So in this case, the programmable data planes with the P4 device will actually be deployed at edge, the edge of like so the border gateway of the edge. So it's a single device, and it can run at line rate. So if your question is related to what happens if you have multiple edges or multiple set devices at a single edge. So in fact, there are multiple different things that you can do. So one is that they're independent and they just deal with the traffic that they would anyway route. And an alternative, so in the case where each of them is actually connected on different next hops, in this case, you can start trying to make them collaborate. But this is not something, so this is something we have discussed, but we have not really, I don't have a, have not conversed on that.
Yeah, I see. Very cool. Yeah, thank you.
Hi, I'm Qizhen from Stanford. I might not be doing load balancing well because I also have a question for the end-to-end routing paper, but this question might be of interest to other panelists as well. So I think most of the innovations in real-time applications are currently in transport application layers. So I guess one of the potential reason I was imagining is when you're working in the internet layer, you might be interacting with all these ISPs and other potential agents, or so there could be some other potential challenges. So one thing I was imagining is that when you're doing end-to-end routing, some of the ISPs might be unhappy because they might get less traffic in their some of their servers because you're just doing it just using two different nodes instead of all the paths in the middle. So I was wondering if you have like would there be like similar challenges if you're trying to deploy this system on a large scale basis?
So that's a great question. I can start and then add something. So in particular for Tango, we actually don't need the permission from any other AS. And that's because we're basically hacking BGP, so with BGP communities. So that's great because we really don't want anyone but the other operating to play with us. But like you're actually raising a very interesting point, and that okay, would certain ISPs be unhappy because we are actually using their paths? So that's an interesting question, but I think if they really have to play the performance, and then we don't use them anyway, which is something that is not really created by our system. But in general, I think this ability of really using different ISPs, it would be actually happy if their network is used more. But this ability to actually do it without with explicit cooperation of everyone, and like while playing with BGP, like in a backwards compatible manner. This is really
Thank you.
Hi, this is Tal from UT Austin. And I have a question for the full stack SDN work. So I wonder what comment you have on the availability of runtime programmable switches, and how does that fit into this this kind of being able to identify the incremental part of the program, and can they be combined together?
May I? All right. So if I understand the question correctly, so you're wondering what happens to a solution like the full stack SDN when you want to change dynamically the programs running on the switches. Is that correct?
Yes.
All right. So I think these two are kind of at odds with each other, because if you look the way the solution is proposed, you actually supply all three programs, the control plane, the management plane, and the data plane. You compile them, type check them together, and then you deploy them. So if you change your data plane program, suddenly it won't type check with the rest. The structure of the relations that the control plane manipulates will change. So I think more work is needed in order to accommodate dynamically changing programs. Yes.
I see. Thank you.
So I have two questions for you guys. So the first question I have is for the first three talks of the session. So if each of you were to imagine the other papers being deployed, what would that mean for your solution? Like, can you comment? Do you think what would happen?
So uniformly, it would be a better world for all, I'm pretty sure. So let's see. So just flashing back, second talk was on distributed verification. And yeah, so verification is a very complementary task, right? So we want to establish that what we're deploying is correct. And what I talked about is that we want to establish that what we think we're deploying is what we're deploying, which should also be correct. And then the talk after that was a full stack SDN. And it was about a more cohesive way of programming the network. And there again, yeah, I think it's very much in concert with the previous two talks, right? Because it's partly targets that operational problem of having joined up behavior in the network, making sure that the left hand knows what the right hand is doing when these different layers are programmed potentially by different overlapping teams, right? It avoids nasty, nefarious bugs that you can have because of the lack of maybe type checking that would implicitly have been carried out hopefully by a human, and delegating it instead to a machine. So I think that's my take.
Well, a network has two components, right? It's the static programs that run in a network, but it's also the control plane state, which changes dynamically. And I think that some of the verification problems address also dynamically changing control plane state. So so having given a full stack solution, I won't help with that too much. But I think I want to make a point. So even if you don't believe in P4 and programmable data planes, P4 has proven useful because it actually gives the semantics for what the data plane is doing. So companies like Google use P4 to model what non-programmable speeches are doing. And I think it's very beneficial if you can give more semantics to what each of the planes is doing. If you have a precise specification of what each of them is doing, then they become more amenable to verification and all sorts of testing and automation tools.
Yeah, just to comment, to answer your question, I agree. I think the previous comments, right? I think the approach are very complementary, like remote attestation and distributed verification are complementary. And for the full stack SDN, so I think like distributed verification can allow to catch like bugs, can be like software bugs or hardware failures, basically. So I think that the three of them can definitely like go very well together.
So my next question is for Maria. So the way the problem was pitched is as a way to compete with basically clouds that are getting closer and closer to the edge, and they're basically taking the edge's traffic, right? So do you think this competition is actually winnable in the sense that the clouds have a centrally managed WAN, which they can basically continuously optimize for performance and better performance? So do you think you can ever get to performance that actually matches what you can get if you go over the cloud WAN?
That's a very interesting question. And our goal is not really to compete. But what is important is that we need to remember what Via said yesterday. It's not only about US or America, right? There are some there are networks that are not as well served, and there are also enterprises that might not have Azure tool that's next to them. And even if they have them next to them, so I want to really actually, I'm not sure when we decided that just because some companies end up being so close to the edge of so many networks, that's the great internet that we actually want to have. So we're not really competing, we just want to provide an alternative that would allow smaller enterprises to actually be they would actually be able to compete with, say, have a data center. You should be able, even though your network, you don't have a private one, to actually serve your clients. So it's more about equity and providing, fighting a little bit of consolidation, providing alternatives rather than competing directly. And I want to add something to that. Even if you see, today we have so many distributed applications that are run on top of the internet, blockchains and everything, and people are working really hard to prove properties on those systems, but and they're supposed to be decentralized, but they end up being hosted in one or two providers. So this is something that it's we don't like, these are different communities, so they're not necessarily understanding what that means. But I think it's really important, like that we don't give up on the internet itself just because there are three hyper giants that provide connectivity for most of the users.
You also have a question?
Hi, I'm shooting from UC San Diego. I guess that's this question is for the first two paper about the attesting. Yeah. So it's like so it's if the topological like the topology change in the network, like will the thing fall into like a limbo transient state? Like how would you like incorporate that? Like if something is like topology is changed.
Hi, yeah, great question. So that goes to the heart of one of the extensions to Copeland, right? So Copeland is not able to reason about topologies that change, and that makes it brittle and makes it somewhat less suitable to use in realistic settings. So one of the things that we're melding to it is quantifiers over paths so that we don't have to specify the paths. But there is, so the short answer to your question is that the statement, so the query in order to get this evidence would still be satisfiable by whoever is delivering the traffic. One interesting thing to consider, so short answer is yes, but I'd also like to give a slightly longer answer if I may, is you might have equipment along the way that can't attest, right? So in the perfect world, there would be a certain degree of homogeneity across heterogeneous devices, that there's a certain kind of baseline that everybody meets. In reality, what you are going to likely see is that there is going to be some equipment that can attest and some equipment that can't attest. And again, this is a reality that is somewhat imagined at the moment, right? So imagining if we can have that, it's kind of the prevalence of equipment that can attest. You might not have full visibility across the path. So, the paper goes into that about on how to mingle together segments along the path where you can have attestation and other segments that you don't, and what happens at the boundary of the two. In case you're interested in finding out more.
Thank you. Yeah, I also got one more question for Tango. So I think like for Tango, there's an assumption that it needs to be a programmable switches to like have that solution working. I think the solution itself is elegant, but I'm challenging the necessity of actually using the programmable switches because they're more expensive than like dumb switches.
No, so in fact, that's not a necessity. It's rather something that would make sense as a solution. It would add some like capabilities. So basically our prototype and which runs on top of the like public internet and gives 30% improvement in latency. This is only on UPF. So that's a straight answer, no. But like if you actually want the traffic to be like to scale at terabytes, like of course, then you need something.
Okay, I think I just misunderstood it. Thank you.
Let's thank the panel.